And today we will see in detail the Dirac relativistic equation. Before going into that, we know the problem with the Klein-Gordon relativistic equation. Mainly it has negative probability which is practically not possible, and it has negative energy but no explanation for negative energy, and we have to take square root of the operator. Also the spin is excluded. We will see how Dirac handled this method in a very beautiful way. So we will see the Dirac modification step by step. The Schrodinger equation in the case of relativistic is p squared e squared is equal to p squared c squared plus m squared c power 4. This can be written as you take c squared outside. If you take c squared outside, you will get p squared plus m squared c squared. So then EC squared can be written as, here I am taking this into three part, XYZ direction, Px plus Py uh, plus Pz. So I have replaced this P squared as Px squared, Py squared plus Pz squared. In fact, Px squared, Py squared, Pz squared plus MC squared. So then we can write this E squared is Dirac introduced to two matrices. In fact, it is four matrices. Three matrices: alpha 1 squared, alpha 2 squared, alpha 3 squared, and beta squared. Because this is not involved in any operator, so this is beta matrix, this is alpha matrix. So uh, if you want to exactly match the above expression is original one, then alpha I squared must be equal to 1. Similarly, beta squared also must be equal to 1. Then only you will get back your original expression. Now we will see how we are going to achieve this. Dirac developed it in a very nice way. So we got this equation. I am going to just rewrite this one. So I am taking this as C alpha 1 px plus alpha 2 py plus alpha 3 pz plus beta mc power whole square. So this will become C squared. I am multiplying same twice. That is alpha 1 beta px plus alpha 2 py plus alpha 3 pz plus beta mc. I am multiplying this. So I have to get back the original one. First, if I multiply this and this, what will happen? I will get to beta squared m squared c squared. I will get the last term of the original equation, this one. So for all other multiplication, cross term must be equal to 0. Say for example, you take alpha 1 beta, this one alpha 1 beta, then beta alpha 1. So if you multiply the alpha and beta term, it must be equal to 0. That is alpha 1 beta plus beta alpha 1 must be equal to 0. This term must vanish. Similarly, alpha 2 beta and beta alpha 2 must be equal to 0. Generally, I can write alpha I beta plus beta alpha I must be equal to 0. This is anti-commutation. This relation is called anti-commutation relation. In order to get our original last term, that is p squared m squared c squared, the alpha I must anti-commute with beta, which is equal to 0, so that all cross term, that is alpha beta, multiplication of alpha beta terms will vanish. Only this last term exists, all other terms vanishes. So we got the last term as it is. Then we will see about alpha 1, alpha 2, alpha 3. So we have seen, in order to get the last term, that is beta squared, m squared, c squared, we have to impose the condition that anti-commutation of alpha I with beta must be equal to 0. This plus indicate anti-commutation. Now we have to avoid this cross term of alpha I2. So say for example, if you multiply alpha 1 px and alpha 1 px, you will get alpha 1 squared px squared. All other cross term must equal to 0. Say for example, you take first alpha 1 and this alpha 2. Must be vanishes. How it is possible? See alpha 1 here, you are taking here this one alpha 1 alpha 2. Similarly, what is alpha 2 alpha 1 plus alpha 2 alpha 1 must be equal to 0. Same is the case alpha 1 with alpha 3. So you take this alpha 1 and this alpha 3, alpha 1 into alpha 3, and here you have alpha 3 into alpha 1, this one. That is alpha 3 alpha 1 must be equal to 0. Same is the case with alpha 3. So in general, alpha I will anti-commit with alpha j. This plus symbol indicate anti-commutation. That is alpha I alpha j plus alpha j alpha I must be equal to 0. That is alpha I alpha j must anti-commit. So all cross term of alpha I will get cancelled. So now we will get back the original term. So in order to get to original expression, we need three things. That is alpha I and alpha j must anti-commit, and alpha I beta will must be anti-commit. Also that alpha I square must be equal to 1. Similarly, beta square is equal to 1. That is simply alpha squared which is equal to beta squared is equal to 1. So three condition must satisfy. That is alpha I squared which is equal to beta squared which is equal to 1. This is one condition. And alpha I must anti-commit with beta. Similarly, alpha I will anti-commit with alpha j when I is not equal to j. So these are the three conditions in order to get back our original expression. So we have started with this expression E squared is equal to C squared c squared alpha 1 squared beta x squared plus alpha 2 squared py squared. So not beta, px squared, this is py squared. Then alpha 3 squared pz squared plus beta squared m squared c squared. So this we have written as rearranged and rewritten as C multiplied by alpha 1 px, alpha 2 py plus alpha 3 pz plus beta mc whole square. Under the three conditions which I have mentioned earlier, you will achieve this one for alpha and beta matrices. So if you take square root both side, you will get E which is equal to alpha 1 pxc plus alpha 2 pyc plus alpha 3 pz c plus pmc square. Here you can see the energy operator is first order time derivative, as you know very well. Energy operator is first order time derivative. TH I H cross T over T delta T delta over delta T. What is P? P is I minus I H cross delta over delta X. Now you can see both are first order derivative with respect to time and with respect to position. In the case of Klein-Gordon equation, both are second order derivative. That is the major difference. So we have eliminated second order derivative and we brought into first order derivative. Of course, Dirac has done this in a beautiful way. So there are four matrices, one, two, three, four terms. So the total wave function can be written as column vectors psi 1 of R and T, psi 2 of R and T, psi 3 of R and T, psi 4 of R and T. Then we will discuss it further. So far, we have seen three conditions. Alpha I squared, which is equal to beta squared, must be equal to 1. And alpha I anti-commit with alpha j when if I is not equal to j. And the third condition is alpha I and beta will anti-commit. Now we will see the condition one by one. First, we have alpha I squared must be equal to 1. You take the second one, alpha I and alpha j anti-commit. So, if you think of Pauli spin matrix, the properties of Pauli spin matrix is the square of the Pauli spin matrices are 1 and each Pauli spin matrices anti-commit with each other. So naturally, you can take Pauli spin matrices, alpha matrices as Pauli spin matrices. Now you can realize how Dirac cleverly designed this. So no doubt that alpha must be Pauli spin matrices. So alpha I can be written as O sub 2 diagonal element is O sub 2 and the these elements are sigma I. Sigma I is Pauli spin matrices where I is equal to x, y, z. Pauli spin matrices is 2 by 2 matrix. So here 2 represents 0, 0, 0, 0. So null matrices 2 by 2 matrix. This is 2 by 2. So totally you will have 4 by 4 matrices. You remember that the Dirac relativistic equation has four wave functions. I have just mentioned it. So from first and second property, we come to the conclusion that alpha I is equal to Pauli spin matrices. Then what about beta? Here it is very interesting. Beta square is equal to 1. So, beta square is equal to 1, alpha I and beta anti-commit. If beta squared is, beta is identity matrix, what will happen to this? Beta is identity matrix, then alpha I beta plus beta alpha I equal to 2 times alpha I. Which is not satisfying this anti-commutation relation. Then what to do? So that also Dirac cleverly formed that the upper diagonal element I2 is identity matrix, that is 1001. And then lower minus I2, that is lower matrices is minus 1 0 0 minus 1. So now we have found the solution for that also. So if you add both, because upper diagonal element is identity matrix. So lower one is a minus of the identity matrix. Then here another there is another meaning also. So half of the particle will have a positive charge and another half will have negative charge. I will come to it later. So Dirac cleverly solved this also. Now this will become zero. Uh, we will go further. So we have seen alpha is equal to O sub 2, 0 sub 2, sigma I 0 sub 2, and beta equal to I2. This indicate, as I said, 2 by 2 matrices, and 0 sub 2. 0 sub 2 minus I sub 2. So sigma x alpha x is equal to sigma x, which is 0 1 1 0, 0 1 1 0, because this is upper half diagonal, this is lower half diagonal matrix. So similarly alpha y is equal to sigma y, 0 minus I 0, 0 minus I 0. Then alpha z is equal to sigma z. So 1 0 0 minus 1, 1 0 0 minus 1, and beta matrices is I sub 2, that is 1 0 0 1, and here minus 1 0 0 minus 1. Here you can realize this matrix, uh, 2 is plus 1 and 2 is minus 1. So 50% of the particle is having plus 1 and another 50 is minus 1, 50% I mean. So Dirac explained that the negative energy of the particle is due to antiparticle. He introduced the concept of antiparticle. That means a particle is having same mass but opposite direction, which is called positron. I will come to it later. Now we have to find the probability of Dirac relativistic equation. E is equal to alpha Pc plus beta mc square. As I explained earlier, here energy is I h cross delta over delta t, first order time derivative. Uh, P also first order partial derivative. Now you replace this equation by its operator. E equal to I h cross delta psi over delta t, and the right hand side, this P is equal to minus I h cross delta psi, of course, C alpha I, so C times alpha I. If we take complex conjugate of it, this plus will become minus and this minus will become plus. So first what I am going to do is, anyway finally we are going to cancel this constant. So you do it right now. This will get cancelled naturally when you subtract this from this. Now you subtract this and this. What will happen? The first one is before that you rewrite this. I have removed the second term. So I h cross you multiply this by psi prime. So I h cross psi prime delta psi over delta t is equal to minus I h cross c psi prime alpha I delta psi. Similarly here you multiply by psi in the right hand side. Here is always complex conjugate will come into the left side. Here psi will come to the right side. So you multiply in the right side. So this will become the term I h cross c delta psi prime alpha I psi. So now you subtract this from this. So you will get I. Before that you can cancel I h cross, I h cross, I h cross, this thing, I h cross. So this will become psi star delta psi over delta t plus minus of minus will become plus plus psi delta psi star over delta t. Then what about the right hand side? Minus c, you take minus c outside. You have psi star uh, alpha I delta psi, then delta psi star alpha I psi. This can be written as, and you can bring this to the left hand side, this can be written as minus, when it comes to other side it will become plus, minus C divergence of psi star alpha I psi, which is equal to 0. Here from the continuity equation, this is equal to Tp over Tt is equal to plus divergence S current equal to 0. Here S is equal to C psi star alpha I psi. You don't worry about it. What about P? P is psi star psi. So this must be real and positive quantity. Unlike a Klein-Cardan equation in which we got E over mc squared multiplied by, you remember that, psi star psi. Since in Klein-Cardan equation E can take negative value, so this is probability. So the probability can be negative, but whereas here the probability is always positive. That is one of the advantage of Dirac relativistic equation. So now we will summarize our result and compare the Klein-Cardan equation and the Dirac relativistic equation. One of the most groundbreaking feature of Dirac equation is its prediction of antiparticle. So antiparticle, I told that you will get negative. 50% of the particle is having positive energy, another 50 is negative energy. For every particle, there exists a corresponding antiparticle with the same mass but opposite charge. The example, electron and positron. Positron is having the same mass of the electron, but uh, charge it is minus negative charge. This is positive charge. So this confirmed experimentally with the discovery of the positron in 1932, validating the equation predictive power. So the Dirac equation defines a probability density P equal to psi star psi, that is always positive and conserved. Uh, this resolved the issues with the Klein-Cardan equation, which allowed negative probability due to the second order time derivative. So here it is first order time derivative. And most importantly, it includes spin also. So these are the advantage of Dirac relativistic equation over the Klein-Cardan equation. Thank you very much for watching my video and supporting me continuously. Thank you very much.